It's a great pleasure to be here. Thank you so much for inviting me. I want to give a talk that's somewhat different from the usual distinguished lectures that people give. When somebody gives a distinguished lecture, it's usually a very high level talk, and there's not a whole lot of technical content to it. I want to give a very different talk. I want to talk in some depth about a subject that many of you might be a bit surprised about because it's a somewhat old-fashioned subject, and that is the parsing of context-free languages. This is not an area that I do research in at this point. My own research is actually in parallel languages, compilers, runtime systems, that sort of thing. So I do at UT Austin what Nancy and Lawrence do so well over here. But all of us who work in programming languages have to teach compiler classes every once in a while. And if you've ever taught a compiler course or you've taken a compiler course, you know that that 2 to 3 week period when you talk about parsing is one of the most difficult times during the course. And that's because even though there's been a lot of work on parsing, somehow it doesn't all come together in a very nice, smooth way. So that's essentially what my talk is about. It's about a new way of thinking about parsing, a new way of teaching parsing, a new way of learning parsing of context-free languages. We call it Parsing with Pictures, and it's joint work with Gianfranco Bilardi at the University of Padua in Italy. Let's begin by recalling a little bit of historical context. So we think about context-free grammars and parsing of context-free grammars as a 20th century activity that was motivated by the invention of the digital computer, high-level programming languages, and parsing of programs in high-level programming languages. However, if you talk to your friends in linguistics, they'll tell you that rule systems similar to context-free grammars were used a very long time ago to give a formal grammar for a natural language, in fact. So they were used as far back as 500 BC by the great Sanskrit grammarian Panini. Not panini, which is Italian for bread, but Panini. Now you might wonder why Panini and the people who worked with him bothered to formalize the grammar of a natural language, something that no other civilization would do for another 2,500 years. Well, Sanskrit is a language in which Hindu prayers are written. And back then, there was apparently a belief that unless these prayers were chanted by the priests, the Hindu priests, precisely and correctly, the gods in heaven would not listen to these prayers. And so somebody came up with this great idea that if one could formalize the grammar of Sanskrit and teach that grammar to all the priests, then they were less likely to make mistakes when they were chanting these prayers. Whether the gods actually listened more carefully to those prayers or not after the invention of these rule systems to describe the grammar of Sanskrit is, of course, unknown. But if we fast forward by another 2,500 years, then we get to the 20th century. And then we have this explosion of work between roughly 1950 to the mid-1980s. So a lot of very distinguished people. This work was started by Chomsky at MIT, his famous paper on the Chomsky hierarchy, followed up very soon, a couple of years later, by John Backus, who invented the world's first high-level programming language, Fortran. And of course, he had to have a parser for programming Fortran programs. And so that's how people got interested in parsing. And then later, this was followed up by a lot of work at the interface of theory and programming languages. So people like Backus Naur, John Koch, Niklaus Wirth, really a whole lot of people. I think it's fair to say that probably more Turing Award winners have worked in the area of parsing than have worked in any other one area of computer science. And during those 30 to 40 years, these distinguished people invented many parsing algorithms. So for parsing general context-free grammars, which could be ambiguous, we have Earley's algorithm and the Koch-Kasami-Younger or Koch-Younger-Kasami, CKY, CYK parsing algorithms. These can take cubic time, so cubic in the length of the input string that you're trying to parse. That's too long for most programming languages, for most compilers, and so people invented subclasses of context-free grammars, which in particular are unambiguous. And for those subclasses, we can actually do parsing in linear time. And that's what led to this alphabet soup of grammars and languages that we use to torment all our students with: SLLK, LLK, SLR, LR, LALR, and so on and so forth. At this point, all these algorithms have been around for many years. There are books on parsing, encyclopedias of parsing, and so on. And so you might wonder, well, what remains to be said, right? Maybe all we need to do is just read those books. Well, if you've ever tried to teach from one of those books, then I think you'll sympathize with me if I say that the concepts and the algorithms, the way they are described in the standard presentations, are actually quite hard to understand. So here, for example, is a definition of a LR0 grammar. It's from Hopcroft and Ullman, but you'll find the same definition in every other book. And part of the definition says something like, for every viable prefix gamma, whenever a arrow alpha dot is a complete valid item for gamma, then no other complete item nor any item with a terminal to the right of the dot is valid for gamma. Now, I'm sure if you talk to Hopcroft or Ullman or some of these people and say, well, you know, this is a bit non-intuitive, they'll probably be surprised and say, no, it's very intuitive to us. All I can tell you is it's not very intuitive to me. I have difficulty with this every time I teach this subject, and therefore I'm sure that all of my students also have difficulty with it. Another thing is that the way the standard presentation of parsing algorithms goes, the connections between different grammar classes and algorithms get obscured. So the way that SLL and LL parsers are presented, you present them using recursive descent. You write a bunch of mutually recursive procedures that call each other and end up parsing the string that you're interested in. That's completely different from the way that we present SLR and LR parsers. So for those, we use something called a shift-reduce automaton, and then there are big parsing tables that you have to build with conflicts and so on and so forth, and resolving those conflicts with look ahead. So really, it's described in a totally different way from the way in which we describe parsers for SLL and LL, even though both are just subclasses of context-free grammars. And the same thing is true even for these other algorithms. So CYK or CKY, for example, that's presented using dynamic programming. So another paradigm there. Earley's algorithm is presented using closure rules. And so at some level, all of these are parsing various categories of context-free grammars. So you'd think there'd be connections between them, but those connections, even though they do exist, get obscured by the standard presentation. And along the same lines, even though every regular grammar is also a context-free grammar, again, the way that the parsing of regular grammars is presented is completely different from the way we talk about parsing for LL or LR or CKY, Earley, etc. What do we do for regular grammars? Well, for regular grammars, what we actually do is to build a graphical representation of the regular grammar, namely a non-deterministic finite-state automaton. And then the parsing problem for regular grammars essentially reduces to following certain kinds of paths in this non-deterministic finite-state automaton, following certain kind of paths in the graph that we build. So we use a graphical representation, and again, this looks completely different from the way we think about parsing for context-free grammars, even though every regular grammar is also a context-free grammar. So one could go on in this vein, but the question, of course, is, well, what are we going to do about it? So here's what we do about it. What we do is to basically reinvent the field of parsing, but using a graphical representation of context-free grammars that we call the grammar flow graph, or GFG for short. So here is a GFG for one of our simple grammars that I'm going to use in my talk. And what you notice is that at some level it looks very similar to a finite state automaton, right? There are nodes, there are edges. Some of the edges are labeled with terminal symbols. The edges that are not labeled with any terminal symbol are epsilon edges. So at some level it looks very similar to a finite state automaton. In fact, here is the connection. Just as for regular grammars, you have a finite state automaton. For context-free grammars, the GFG is going to serve exactly the same purpose. What that means is we're going to take all parsing problems and basically reformulate them simply as problems and following certain kinds of paths through this graph, just like we did for finite state automaton. But it turns out the kind of paths we need to follow are special in ways that I'll make clear in a minute. And The bottom line, though, is that basically all parsing problems become path problems, and parsing algorithms just become algorithms for solving these path problems in the GFG. So you have a graphical representation, which in my opinion is much more intuitive and easier to understand than the standard approach for talking about parsing. And so the advantages that we see: concepts and parsing techniques become easier to understand. So many very complicated algorithms in the standard way of presenting, I'm going to show you on a single slide. And then you'll tell me after I present that whether you understand it or not. So that'll be a test for me, not so much for you. And then unexpected connections emerge between different parsing techniques, algorithms for regular grammars and context-free grammars, and also front-end and back-end algorithms in compilers in a very strange way. So that's essentially where we want to go. In case you've worked in this area, if you're in natural language processing, for example, some of the things I'm going to talk about may seem familiar to you. So in particular, there's some work by Woods way back in 1970. So he defined a graphical notation for context-free grammars that he called recursive transition networks. The GFG is really very different. The way you think about the GFG is quite different from RTNs, and I'll explain that later towards the end of my talk. In the theory community, Yannakakis defined something called CFL paths, which again is going to be related to the kinds of things we do, although again the paths that we're going to follow in this graph are different from CFL paths. I just want to mention these because I've given this talk in the past, and people who know these two concepts look very disturbed and say, well, do you know about this work? And yeah, I do know about this work, and what we do is different. We're not reinventing the wheel. So here's how my talk is organized. We'll begin by talking about the GFG. So given an arbitrary context-free grammar, how do we construct the GFG? We'll talk about an interpretation of that graph that I call the non-deterministic GFG automaton, or NGA for short. So it's the context-free analog of a non-deterministic finite-state automaton. And then we'll talk about certain kind of paths that we need to follow in this automaton that we'll call complete balance paths. So we're going to introduce those concepts. Then we'll talk about how to parse general context-free grammars. So the grammar could be ambiguous, as complicated as you want to make it. I'm going to develop an algorithm for you on a single slide, okay? And then we'll talk about look ahead, and then we'll talk about parsing for subclasses of grammars, so LL and LR grammars. So it turns out that the GFGs for LL and LR grammars have certain structure that you can exploit in order to do the recognition and parsing in linear time rather than in cubic time that you would require for general grammars. So doing all this is actually much more than what is taught in about 2 to 3 weeks in a compiler course. So if I had 2 weeks, I would actually do all of this. But you probably don't want to sit here for 2 weeks and listen to my lectures. I have exactly 1 hour. So here's what I'm going to do. I'm going to do the first 2 things in detail, and then I'll sketch these 2 points over here to tell you about how to think about look ahead and how LL, LR, and so on in compilers can be thought of in terms of the GFG. And I'm happy to either talk to you afterwards if you want details. We also have a tech report on this. Okay, so first order of business, what is this GFG? And so here is how I want to explain it. I want to take a very simple context-free grammar from the Dragon book, in fact. So there is the grammar. S is the start symbol, so there are 3 non-terminals, S, A, and B, and S has 4 productions, and A has 1 production, B has 1 production. So given this context-free grammar, which is very simple, but the construction I'm going to show you works for any context-free grammar. Here's what you do. The first thing that you do is you introduce what we're going to call start and end nodes for each non-terminal. So here the non-terminals are S, A, and B. So you're going to have a start node for A, which I'm going to write as dot A. And the dot tells you I'm about to recognize an A. The end node for A will have a dot at the end. So A dot saying at this point I've completed recognizing an A from the input. So for now, I just have these 2 nodes for A, similar nodes for B, and then I have dot S and S dot for S. Okay, So that's very simple. Now what I want to do is I want to take a production, A arrow D, and then convert it into a portion of this graph. So intuitively, what's going to happen is if I have n grammar symbols on the right-hand side, I'm going to have n plus 1 nodes. And those nodes are going to form a chain, and I'm just going to put them in a chain and connect them from dot A to A dot. So this is very similar to what you do for finite-state automaton. So here is the way you do it. So I have only one grammar symbol, namely D. So I have two nodes over here. And then this node is labeled with D, just like for finite-state automaton. And then I just connect the first node to dot A and the last node to A dot using epsilon edges. So this should look very familiar. This is what we do for finite-state automaton, so nothing very special going on over here. Now it'll turn out that for the presentation, it'll be convenient to give some names to these nodes. And I could call these nodes anything at all. I could call them Joe, Lawrence, Nancy, Jennifer, whatever. But it'll be convenient to give them more systematic names. And so here is how I want to name them, just so that we can talk about them. I'm going to use this dot notation, and I'm going to say the very first node will be labeled by A arrow dot D. So intuitively, I'm trying to use the production A arrow D, and I'm at the beginning of this production. After I've eaten up a D from the input, that's one way to think about it, the dot moves over. And so if I have n symbols, the dot basically just keeps moving over by one. So that's how you get n plus 1 nodes over there. Fair enough? Any questions? Let's make this interactive. I'm happy to take questions on the fly. Yes?
I'm sorry if I'm just not being smart enough, but I didn't really understand what the period represents.
Don't be sorry.
The period is just part of my notation, and it represents where you are in using this production, right? So you're using the production A arrow D to do some work, and the dot represents, well, I'm at the beginning of using this production. And then after you've consumed a D, you've recognized a D from the input, you move it over by one to say I'm done. When you get here, you say, well, I'm done recognizing an A. So that's the way you're going to think about it.
So that's just for the slides, not for the implementation?
Just for the slides. That's right. It's just a way for us to talk about nodes in a systematic way. What I do in the end may not make any sense, but at least I'm consistent in what I do. All right. And now there's only one thing that I need to tell you about, and that is what to do when you have a non-terminal on the right-hand side, right? Everything else you know what to do. So let's take the production S arrow capital A little a. You have two grammar symbols, so you would expect to see three nodes, the first with a dot before AA, then moving over, etc. So here's what it's going to look like, but it's going to look a bit different from what we did for this case over here. So you can see you have three nodes over there. The dot just keeps moving over by one every time around. This is just a terminal transition, so that's labeled with A, same rule as here. But here, I need to move the dot over a non-terminal. So the way to think about it is, think about this as a little procedure that says, you know what, I need to recognize an A at this point. I don't know how to do it, but I have a buddy who knows how to do it. So I'm going to call that buddy. Sorry?
Capital A specifically.
A capital A, that's right. So I'm going to call this guy over here. So it's like phone a friend in that Who Wants to Be a Millionaire. So this guy does its work, and then control returns back over here, and then you continue. So anytime I have a dot before a non-terminal, I'm going to connect that over to the start symbol for that non-terminal, and then from the end symbol, I have an edge coming back. You should think about these intuitively as call and return edges, okay? Because that's sort of what they are. Now, if you literally implement them as call and return edges, it turns out you can't parse general context-free languages for reasons that will become clear later. But the intuition is essentially, it's like you make a call and then you make a return. So in fact, these edges will come in matched pairs, just like in an interprocedural control flow graph, right? Call and return edges are matched to each other. And then that's the rest of the GFG. So here, if you look at this, you have dot BAC, so you're doing this one. So moving over a little b is just a terminal transition. Now I need to move over a non-terminal. So using my rules, I have that, and then over the c, etc. Okay? So at this point, you know how to construct a GFG. Yeah?
If it's okay.
Yes, absolutely.
So when it gets to the bottom of that capital A chain, for example, how does it know whether to take the red path or the green path?
Okay, you've asked the $1,000,000 question. Good.
Same over there with the B and the red and the blue.
Yeah, absolutely. So the question that you're asking now is, if you look at this particular graph over here, right, there are nodes that have fan out. So start nodes have fan out, right? And similarly, end nodes also have fan out. So what rules am I going to give you in order to traverse the graph? And that's what I'm going to do next. So just hold on to your question. You asked exactly the right question at this point. But this is what the graph looks like. Now I want to give this an interpretation. Before I do that, I want to introduce a little bit of terminology. We already talked about a start node and end node for a non-terminal. The very first node for a production, I'm going to call the entry node for that production. The last node, I'm going to call the exit node. I'm also going to talk about call and return nodes. So a call node just has a dot before a non-terminal. So this is the call edge. The return node has a dot after that non-terminal. So again, call and return nodes come in matched pairs, just like in our interprocedural control flow graph, for example. Okay, and then I'm going to make a couple of simplifying assumptions that don't really change anything. So I'm going to assume there are useless non-terminals. That means every start node is reachable from dot S, and then from there you can reach S dot. So that's very easy to do. And then I'm also going to assume that the start symbol doesn't occur on the right-hand side of any rule. If it does, you just add a new dummy start symbol, S prime goes to S, and you're done. So these are just details, but you don't need to worry about them unless you work in automata theory. Okay, now I want to show you the interpretation of this graph, right? So suppose this was a finite state automaton. So I told you, think about this as a finite state automaton, and now tell me what strings does it recognize, okay? So what you would do is you would take this as the start node, and then you would just find some paths. So trace some path to S dot. You take that path, and then whatever symbols you see along that path, that would be a string in the language. So here it would be B, followed by D, followed by C. So BDC is a string in the language. But notice that if this was a finite state automaton, you're also allowed to follow this path. You come in on the green, and then you leave on the red. And then you go down over here. So BDA would also be a string that you would be allowed to recognize in this language. We want to disallow those kinds of paths, right? We want to disallow those kinds of paths because if you think about it intuitively in terms of calls and returns, right, which is the intuition I want you to have, it's like you made a call along the green edge, so you need to return along the green return edge rather than wandering off somewhere else. The way that Chomsky describes this, he says, a finite state automaton is Markovian. It doesn't have any memory. Whenever it's at a node and there are a bunch of choices, right, outgoing edges, it just randomly picks one and keeps going. We can't be Markovian over here, so we need some memory. So how do we do that? So here's what we do. What we're going to do is restrict ourselves to following what we call complete balanced paths. So a complete path is a path from dot S to S dot, no big surprise there. But a balanced path basically says, if I look at the edges on that path, and I think about each call edge with a certain color as an opening parenthesis and the return edge as a closing parenthesis, then these open and closed parentheses form a balanced string. So in other words, I'm allowed to follow this path, for example, but I'm not allowed to follow that path. Or, for example, coming in on the red, leaving on the green, and so on. So the question is, we need some mechanism now to ensure that this non-deterministic automaton only follows complete balanced paths. So how do we do it? Well, here's the rule for the automaton. It begins at dot S. It finishes up at S dot. It maintains a stack on the side. At start nodes, it simply makes a non-deterministic choice, right? So if there are multiple productions for a given non-terminal, you just non-deterministically pick one. That's the way you think about it. So at start nodes, you simply make a non-deterministic choice. Now, at a call node, like this one, for example, what you do is you push the matching return node on the stack. And then you continue. And now, to answer your question, what happens when you come to an end node? Well, an end node may have multiple edges going out of it, but there's no free choice over there, unlike in a finite state automaton. What the automaton, the NGA, is required to do is it pops that stack, takes whatever node is there, and then continues the traversal from there. So that's how the stack enters into this way of thinking about it. It's a way of enforcing that the only paths that you follow are these balanced paths. Okay, and in terms of an interprocedural control flow graph, if you know what that is, this is what we're talking about here is called the interprocedurally valid control flow path. So the calls and the returns are matched. And all it means really is if you make a call from some place in the GFG, when you're done, you must return to the node immediately after that, rather than wandering off somewhere else. Okay? Sorry? Okay, any questions? Yeah.
So when you say that you push the return node on the stack, does that mean what node it needs to look for at the end? Is that what the return node means?
No, we said call and return nodes come in matched pairs, right? So this is like a call node, that's the return node. So for every call node, there is a matching return node, the node immediately after that. So if this was something dot A something something, this would have been with the dot moved after the A. Remember that? So I could go back. I erase the labels because it gets kind of baroque. But if you look at this, this is a call node because the dot is before the capital A. So the matching return node is here. So when you're over here, you push this node on the stack. You do that, and then when you come over here, you say, well, let's pop. That's here, and then you continue. Okay? So it's really a very simple idea at that level. Any other questions? Yeah? Sorry, say that again. Yeah. No, this is a start node. This is an end node.
I think as the same comprehension can be recognized or understood as that interpretation.
As a what? Okay. I'm happy to answer your question afterwards. But okay, so the behavior of the automaton is clear. So it just maintains a stack, and that forces you to begin here, end there, free choice at any start node. So that corresponds to non-deterministically picking a production. And then when you come to a call node, you push the return node so that you know where to go back to. When you come to an end node, you just pop the stack. That's all there is to it. Okay. And then there's a very simple theorem that you can show that a complete balanced path over here corresponds exactly to a parse tree. So given a complete balanced path, I can construct a parse tree that's a standard representation of the parse and vice versa. And intuitively, that's because the choice that you make at start nodes tells you which production was used for that particular non-terminal. Really, that's all there is to it. And then the label of a complete balanced path is a string is the label of a complete balanced path if and only if it's a word generated by the grammar. Unambiguous grammars have a very simple interpretation in this thing. What it says is every string in the language is generated by exactly one complete balanced path. So you can't have two paths, two complete balanced paths that have the same label. That's what an unambiguous grammar means here. Okay? All right, so any questions about the GFG? So you can see why the GFG is really very much like a non-deterministic finite state automaton, except that it has these funny edges, the call return edges that come in matched pairs, and you're restricted to follow only these balanced paths, and that's why you have the stack on the side to do that. Yeah?
Can you give a little intuition behind the proof for unambiguous grammar?
It follows from this, right? So since every complete balanced path, you can construct a parse tree. If you have two complete balanced paths that produce the same string, then that means you have two parse trees that produce the same string. So it's an ambiguous grammar. So it follows directly from that theorem there. So there's a unique path. So it's a very simple, intuitive idea for unambiguous grammars. Okay, so now we've done a little bit of work. So let's now use it for something interesting. So what I want to do now is to show you a parser for a general context-free grammar. Could be ambiguous, could be as complicated as you want to make it. Now, if you go to most compiler people and you say, oh, you know what, can you tell me how to parse general, ambiguous, context-free grammars? They'll say, oh, you know, this is not something we handle in compilers because we only work with unambiguous grammars. In compilers, we mean what we say what we mean. So all of this ambiguity and so on and so forth is, you know, too hard to handle. Maybe you should ask people in natural language processing. They may tell you the algorithms. What I'll show you is you can do this on one slide if you've been following the GFG. So let's do it. So we're going to write a parser for a general context-free grammar, which could be ambiguous. What I'm going to do is to take a very simple grammar, which is actually not ambiguous, but nothing that I'm going to use in the algorithm I want to develop uses that particular fact. So this is just parenthesized arithmetic expressions with integers and an infix plus or minus. Okay, so it's about as simple as you can get. So this is the context-free grammar, and then here is the GFG for it. So this is for the production S goes to E. So the P corresponds to S arrow dot E, and then when the dot moves over, that's the Q. So this is for the production S goes to E. E has 3 productions. So you can see 1 production, 2 production, the third one. And then this is for the integer, E goes to int, production over here. And then this is for open paren E minus E close paren, right? So it's for this production here and so on. So you can see the direct translation to the GFG. Now what I want to do is I want to ask the following question. Is the string open paren 9 plus 6 close paren? Is that in the language recognized by this grammar or not? So what do you guys think? Yeah?
Professor, where you wrote int here, you don't mean literally the string int, you mean any integer.
Any integer, yeah. That's a convention that we follow. So it obviously is, right? So we need to develop an algorithm for recognizing that. So here's what I want to do. First, again, to build up your intuition, I want to forget about the fact that this is a GFG, and I want to treat it as a non-deterministic finite-state automaton. Right? So non-deterministic finite-state automaton, you don't really care what the colors on these edges are. I just follow, if there's some path from dot S to S dot that spells that particular string, then the automaton recognizes that particular string. Okay, so if this was an NFA, what is the standard algorithm for checking whether that particular string is accepted or not by this automaton? So you probably know the epsilon closure algorithm. What you do is you construct a series of node sets. And in the very first node set, which I'll call sigma 0, what you do is you just put the first node, dot S, and then you add all nodes that you can reach using just epsilon transitions, right? And so you can reach P, that's why P is there, and then you can go to dot E, A, G, I. So all of those are in sigma 0, and then you can't proceed any further without consuming something from the input, okay? Then what you do is you read in the first symbol, which is open paren, and then you see which of these nodes can make a transition labeled with open paren. So which nodes can make a transition labeled with open paren? A and I, right? So A can make a transition to B, I can make a transition to J. So the next node set simply has B and J over here, and then you take the epsilon closure of that again. So from B, I can reach dot E, A, G, and I, so you have all of that. From J, it's the same set of nodes, and so on. So you keep going. And the string is accepted by this finite-state automaton if you can actually consume all the input. So in other words, if there are n symbols, you can construct n plus 1 of these sigma sets. And furthermore, if you see S dot in the very last sigma set, then that says there is some path from dot S to S dot that actually spells this particular string. So this particular string is actually accepted by this graph if I think about it as a non-deterministic finite-state automaton. Okay? So this is just the epsilon closure algorithm. right? All of you familiar with this? So Lawrence should have taught you this if you were in his course. Okay, so now what we need to do, you didn't do it.
I want to know how many of my students in 434 are here. Can I see a poll raised? Out of 23, that's all what they are.
Okay, well, we have 3, so it's a start. Okay, so this particular string, open paren 9 plus 6 close paren, then is accepted by this graph if I think of it as a non-deterministic finite state automaton. But what you notice is that S dot also occurs in sigma 2. So in fact, open paren 9 is also accepted by this particular automaton. And that's because there is a path like this. You come over here, open paren 9, and then you go out there. So there is a path that spells open paren 9. However, that's not a balanced path. So what we need to do is somehow rule out those kinds of paths from being followed. And if you think about it, what that essentially means is when I see something like a E dot, which is like the end of a procedure call, what I need to know is, well, the only way I reach this E dot over here is by coming in from dot E. I must have made the call to E somewhere for me to be exiting the E dot. So I need to know where that call was made, because if I know where that call was made, then I know where the call nodes are, and then I can simply add the corresponding return nodes. Does that make sense? That's the intuition. So the question is, how do I go about doing the bookkeeping so that I don't follow all paths, but I only follow prefixes of these complete balance paths, right? That's the question. So here's what I'm going to do. What I'm going to do is, whenever I add a start node, so I'm following a bunch of paths, whenever I come across a start node and I add it to a sigma set, I'm going to label it with the number of that sigma set. So if I add the dot E over here, this one would have a label of 1. This dot E over here, when I add it to this, will have a label of 3. And then that label will simply get propagated through all of these nodes to the end node. So when I'm at this end node, if this call was made in sigma 3, then this would have a label of 3. So then I just go back to sigma 3, and I look at the call nodes over here, and I just add the corresponding return nodes there. So that's the intuitive idea. Okay? So let's work through this, and then you'll see how it works. So again, I begin by adding dot S to sigma 0, and then we said anytime you add a start node, you immediately add the number of that sigma set. So dot S0. It's like saying I'm making a call to S over here in sigma set 0. That's where the call is beginning. Okay? All right, and then what I do is I simply propagate that when I go across this epsilon edge. So then I have P with 0 also. Now I come over here, and I have dot E. So then, since this is a start node, I take that label, put a 0 over there. Now A, G, and I. So I simply add A, G, and I all with 0 because that's just propagated there. Okay? Now what I do is I read the first symbol and I just keep going. And so let me just show you a few steps of this algorithm. So I read in open paren. When I read in open paren, I have B and J that get added to this. And then that label simply propagates from A to B and from I to J. So these two also become 0. Now I go around over here, and now I'm adding a dot E. I'm adding a start node to the sigma set, so my rule says that has to be labeled with the number of that sigma set here. So this becomes dot E comma 1, and now A, G, and I all have a label of 1. Now when I get to the 9, I eat the 9 up. The only thing that can make a transition is G, which goes to H. So H gets 1. And now I get to E dot with a label of 1. Now I need to know, since I'm at E dot comma 1, so I'm over here, well, do I take that edge? Do I take all of those edges? Where do I return to? Which was exactly the question that you had asked me way back when. But now I have enough information to answer that question, right? And I have that information because E dot comma 1 says, this call originated in sigma 1. So all I have to do is to go back to sigma 1, and then I look at the call nodes over there, which are B and J. As you can see, that's where the calls originated. So I simply add the matching return nodes, which are C and K. So I add C and K, and I just copy over the labels. So B0 gives you C0, and then J0 gives you K0. So it's a very simple mechanism. This is just tagging. Whenever I begin a start node, it's like making a new call. And I simply label that with the number of the sigma set. Then I propagate that number all the way through from the start node to the end node, so that when I get to an end node somewhere, I know where to find the corresponding call nodes. Right? That's all there is to it. So let's take a look at E dot, comma 3, for example. So this says I'm at E dot, so I'm reaching the end of a call. This call originated in sigma 3. So now the question is, how do I continue the path? Well, this call originated at D with a label of 0, so I would add E with a label of 0. That's what you see here. Okay? And now what is the acceptance condition? The acceptance condition is very simple. If I'm able to consume all the inputs, so in other words, if I can construct n plus 1 sigma sets, and in this last sigma set, I have S dot, comma 0, then that says that I'm completing a call that began at sigma 0, a call to S that began at sigma 0, and then you can show that this basically proves that there is in fact at least one complete balanced path from dot S to S dot. So what have we done over here? All we've done is we've taken the standard epsilon closure algorithm for finite state automaton, and then we added one integer to each entry, right, which was the label of the sigma set. And the rule essentially was, when I get to a start node while doing this epsilon closure, when I add that to a sigma set, I tag it with the number of the sigma set, then I just propagate it all the way through to the end node, so that at the end node, I know how to continue the path that I've been following. Any questions about this? I know this is a bit of a detail over here, but if you understand this, then you can write a parser for an arbitrary context-free grammar, even if it happens to be ambiguous or anything else. It could be as complicated as you want to make it. Yes?
Professor, how do we map from these pairs like I, comma 3 to a node where there's no hex?
Okay, so we have I, comma 3, so where...
That's not a good example.
Sorry? Yeah, well, that's all right. So we'll take I, comma 3. So if you notice I, comma 3, right, you can't extend anything. You can't take an outgoing edge without consuming another input. So what you need to do is to check whether the next input happens to be an open paren. But it's not, because it's actually an integer. And so that particular path that you have followed from dot S all the way to I essentially dies over there. So it's like you're following a set of paths, and then every time I give you a new input symbol, you see whether you can extend those paths. Some paths will die, other paths will branch, but you just keep going like that.
What I mean is the paths that are ambiguous, the paths that could go left or right.
Okay, so this would be an example, right? So what you do over here is, when you get to dot E, right, you add that with a label of 1, and then notice you follow all the paths, right? You have to follow all the edges coming out of it. So you add A, comma 1, G, comma 1, and I, comma 1. So that's how you follow all the paths. So essentially, you're doing the same thing that you do for finite state automaton, except that you're making sure that you only follow complete balanced paths.
So the E at the bottom, E period, how does it know whether to go, which of the outgoing arrows are there?
This one here?
Yes.
Yeah. So what you do is you look at the tag, right? Here it says 3. So that says that the call originated in sigma 3, right? That was our rule. So if the call originated in sigma 3, you simply look at all the call nodes that you have here that are calling E. So notice that the only one is D, right? So then you know the matching return node, which is E, and so that's where you add E.
So that pair on the right that says D comma 0 actually stores invisibly off the chart that is being called for E.
That the return node is E. D is the call node, and so the return node is E. So that matching pair you always have to have somewhere on the side. That's right.
Thank you.
Okay. All right. So at a high level, this is essentially what the algorithm is. I've told you all the details actually. All you have to do is convince yourself that this is right. The interesting thing is this is actually a parser for an arbitrary context-free grammar, because I didn't assume anything about this being unambiguous or anything. I'm just following a bunch of paths exactly like I did for a non-deterministic finite-state automaton, except that I'm just making sure that in the end I'm only following these balanced paths. And I'm doing that by using these tags to match the calls and the returns properly. Okay? Yes?
Is it possible that the width, the size of the pair tokens there could grow exponentially? You have to pass through multiple branch points?
No, you don't. Because you only need one integer always. And the reason for that, okay, so what you're wondering about is when you have a path, you think about having many possible returns because you call, right? And then you want to return. So how is that handled? And the way that's right. No, it doesn't blow up. So you can make do with just a single integer, actually. And the way that happens is when you get to this e dot comma 3, you go back over there, and then you pick up the return node for d, which is e, and then you copy that tag over. When that completes, you know that it's going to start at 0, so then you go back to 0, and then you pick up the return node from there. So essentially, you can go back any number of levels, but using just a single integer, because you always go back, and then that stores the tag that you continue with.
So the list is always bounded by the number of nodes in the graph?
Yes, that's right. Okay? All right, so how many people understand this? Okay, you're either being very kind or I've actually explained this reasonably well. Anybody recognize this algorithm? This is not a new algorithm. This is actually a very famous algorithm, but it's an algorithm that in the standard way of presenting it is so complicated that you don't find it in the Dragon book, except in the bibliography where they give a short description of it, which turns out to be wrong. So even the Dragon book guys, had difficulty with this algorithm in the standard way of presenting it. Remember, these are Aho, Ullman, right? Guys who spend their entire careers doing parsing, literally. It's not even there in most encyclopedias of parsing because it's considered to be an incredibly complicated algorithm. And I'll give you some quotes on the next slide, but I just want to see if anybody recognizes this algorithm. It's a very well-known algorithm. In fact, I mentioned its name before. Daniel?
I'm not going to try it. No.
Give it a shot. You had your hand up. Okay, so this is the famous Earley's algorithm. So it's one of the standard algorithms in the compiler literature. So this is a picture of J. Earley. So he did this work when he was a graduate student at CMU. Okay, so this was in his PhD thesis, and then he moved to Berkeley where he published a bunch of papers, and then for whatever reason he basically dropped out. Right, so this was in the late 60s. So he became a flower child and, went to one of these, this SLN Institute, which is basically a bunch of hippies hanging around and talking about world peace and so on and so forth. So today, the guy actually has his own he's a psychoanalyst. He changed fields completely. So maybe this is what happens if you work on parsing, right? It blows your mind. You do something completely different. So he has his own company, so it's jearley.com, and this I got from his website. So I actually sent him a copy of my paper and said, I'd appreciate any comments. I think there's a simpler way of presenting it than what you had in your thesis. He was kind enough to reply, and he said, it's been a very long time since I thought about parsing. I'm sure you have a nice way. Good for you. And, just move that, right? Okay, so what I want to do is, we don't have the time to go through Earley's algorithm in the standard way, but here's what the Dragon book says. So it says, it's a complex general purpose algorithm due to Earley that tabulates LR items for each substring of the given input, and it turns out that's actually not right. Okay, so as I was saying, even these guys got it wrong. There's a book on parsing, an entire book by Grun and Jacobs. It's a very nicely written book. So they have an entire chapter of about 60 pages on Earley's algorithm, and they call it top-down, restricted, breadth-first, bottom-up parsing. So at this point, I understand Earley's algorithm as well as I understand the road that I take from my home to work at UT Austin, but I still have no idea what top-down restricted breadth first bottom-up parsing means. I mean, it's just, obviously these guys didn't have a clue either. They just made up some stuff and said, okay, that's what Earley's algorithm is. And then they first explain Earley's algorithm without epsilon productions, and then they say, oh, you know, once you throw in epsilon productions, it gets so complicated, stay calm, go out, have a coffee, come back, and so on and so forth. Well, we didn't even talk about epsilon productions. We just breezed right through it because in our way of thinking about it, it doesn't really affect anything at all. If you go to Wikipedia, where a lot of us do our research nowadays, they call it something else altogether. They call it chart parsing with dynamic programming. And it's like, you know, there are all these amazing descriptions of it. If you think about it in terms of the GFG, it becomes amazingly simple. It's just a simple extension of this online simulation of non-deterministic finite-state automata. In other words, this epsilon closure algorithm, where you're just beginning at .s, and you're just following a bunch of paths, right? That's really all we're doing, except that we need a slight mechanism there, the tags, to make sure that you're only following complete balanced paths at the end. So really, you're tracking reachability along prefixes of complete balanced paths. If you get rid of balanced, then that's a epsilon closure algorithm for NFAs. So it's really very simple if you look at it this way. And so you can show that the time complexity of this algorithm is O of n cubed for an input string of length n, and it's n squared for unambiguous grammars. Daniel.
As I recall, I think the standard algorithms for when you have a particular look-ahead are not as bad, aren't quadratic, I don't think.
No, even with look-ahead, Earley's algorithm for if the grammar could be ambiguous, right? For ambiguous grammars, it's still n cubed. But for unambiguous grammars, if you have look-ahead, then it becomes linear time.
So I guess
That's
the
right.
question is, what is yak, right? What's the time complexity of the parser generated by?
That's linear time.
Yeah, so
Yeah. But that's a subset of grammars that it can handle. So YAC can't handle unambiguous grammars, for example. It makes some arbitrary choices when it comes to unambiguous grammars, but it doesn't handle them in a systematic way. So what YAC does is a subset of grammars, which are known as LALR1 grammars. And that's a subset of the class of context-free grammars. Earley has the advantage he can handle any grammar. You throw it at him, he handles it.
It's a proper subset, not everything's in there.
It's a proper subset, yes. That's correct. So in particular, no ambiguous grammar can be LALR1 grammar, right? Yeah.
The grammar that you started with was not LALR. It was LR, but not LALR.
Yeah, that's correct. That's right. That's from the Dragon book. So that's the example.
So the GFG provides an actual different implementation of this algorithm that makes it easier to understand, or it's just a different way to,
It's the same algorithm, okay? That's the amazing thing. It's exactly the same algorithm. It's just that this is a different interpretation because the representation of the grammar is different. So each of these steps you think of in a different way. You just think in terms of following paths.
So would it correspond to a different implementation then if you were to actually write out the algorithm?
Maybe, yeah. So yeah, you would have a graph, you would follow edges and so on. So I actually have a colleague at UT Austin, William Cook, who was, he was designing an ambiguous grammar for a new fancy functional language. And he was going to do all kinds of fancy GLR parsing and so on. But then he attended my talk and he said, you know, if this is all there is to Earley, this is so amazingly simple, I'm just going to do this, right? And so they have a paper now in Popple where they actually just use the GFG and they just follow paths, et cetera, et cetera. If you look at what we do, you can actually translate it into Earley's paper. It's just understanding Earley's paper, you know, as you can tell from these quotes, even the Dragon Book guys found it very hard to understand, right? But it's the same algorithm. So that's a good point. So Daniel.
How did you come up with this? Did you start with Earley's algorithm and simplify it? Or did you come up with this GFG thing and realize it was equivalent? Or what was the process of discovery?
The process of discovery, I started with the GFG, right? Because what I asked myself was, for regular grammars, we have this beautiful graphical notation, right? The non-deterministic finite-state automaton, and everything is so simple over there. So I said, why can't context-free grammar parsing be just as simple? Why isn't there a graphical representation for that? So the graphical representation came first. And then I started thinking in terms of following paths and so on. And then at some point you suddenly realize if all you're doing is following all possible paths through it that spell the prefix of the string that you've read so far, gee, that's exactly like this epsilon closure algorithm for NFAs. It's just you're following prefixes of balanced paths, right? So this came afterwards. Yes?
So how can you put this in context of automating it, like if you have Yak, or Python? There, the beauty is that you just specify the grammar,
Yeah.
and the rest is done for you.
That's right.
Same thing here.
Absolutely. So that's what William Cook and his friends did, actually. So they build a GFG, and then they just do this sort of transitive closure, but following with these tags to make sure you're only following balanced paths as opposed to general paths.
So it
Yeah.
still already exists that's analogous to Yak, but using this as a background
That's correct.
foundation.
That's right. But whether it's available and so on, I don't really know, because that's not my work. That's my colleagues' work. Okay. All right. Let me skip that. Okay. So we are almost at an hour. So let me just say this. Okay. So I want to introduce a little bit of notation, call return paths. So any path in the GFG that's a segment of a complete balanced path, I'll call a call return path. Parallel paths basically say the labels of the paths are identical. And then one way to describe Earley's algorithm for general context-free grammars is that he simply follows parallel CR paths from .s. Right? He's beginning at .s, and then he's following a bunch of paths, all of which spell the same prefix of the word that you've read so far. That's really all he's doing. And then he uses tags to match these dynamic instances of start and end nodes. It turns out that this entire alphabet soup that we've talked about, SLL, LL, SLR, LR, LALR, all of these things, if you look at it in terms of what they do on the GFG, they do exactly the same thing. They all begin at .s, they all follow these prefixes of complete balanced paths. So then you say, well, what's the difference, right? Why isn't everything Earley? Well, the reason why everything isn't Earley is that these grammars, like SLL, SLR, and so on and so forth, have enough structure in them that the GFG is simple enough that you can actually match the calls in the return. So when you're at an end node, you can figure out where the matching call node is without using tags. And that basically reduces the complexity from n cubed to O of n. So basically, there is some structure over there in these grammars that you can exploit when you're following these paths, and that structure is enough to reduce the complexity. So you can look at all of these as optimizations of Earley's algorithm, and that's how it's done in our paper. So this is the kind of unification that's nice, because it says there's a general picture, and then if there's structure, you can actually optimize some of the overhead away, and then you get these other algorithms. Okay. So as I told you, I usually get through what is a GFG and then Earley's algorithm, and I don't usually have time for talking about look ahead or for LL, LR, and what the special structure is. But let me just give you a flavor of look ahead, and then we'll skip to some concluding remarks. So look ahead. What is look ahead? So here's the idea of look ahead. The way that we've described Earley so far, I give you a grammar, you build a graph, and then you take the string that you need to parse, and you just follow a bunch of paths in that particular graph, right? Now, on the other hand, usually you want to write a parser for not just one string, but many strings, right? So if you're going to parse many strings, then it makes sense to pre-process the grammar so that then you can optimize some of the path following that you need to do, right? So this pre-processing time and space is amortized because following all these paths can become a little more efficient. And that's exactly what look-ahead computation is. So the intuitive idea of look-ahead is the following one. If I'm at a point P in the GFG, what are the next K symbols that I would encounter on paths that begin at P? So that's usually going to be a set, right? A set of strings, the next K symbols. And now, if I'm at P, what I can do is I can look at the next K symbols in my input. And if that's not in that set, then I know there's no point in looking further beyond P. So I can kill that particular path off right there at P, rather than going down this blind alley and then later recognizing that this is a useless point. Okay? Very simple idea. And if you want analogy, well, the analogy is right there. I should have had some road signs from College Station, but this is actually from San Antonio. And so if you can see, the road sign says Austin in one way, and then it says Alamo in another way. So look ahead is exactly like taking the GFG and putting up these road signs, saying from this point onwards, if you're here, if you go down this path, well then, here are the symbols that you're going to encounter. And so if the next k symbols in your input are not in that set, there's no point going further over there. So it's like having these road signs on the GFG. And so it turns out that, again, the GFG gives you a very nice way of talking about look ahead. In the conventional way of talking about look ahead, what happens is it's always presented in the context of a particular parsing strategy, like SLL, and then people use that look ahead in other parsing strategies like LR, and then it becomes confusing as to why you can actually do that. For the GFG, it's formulated actually as a simple interprocedural data flow analysis. So let me give you the idea of look ahead, and then we'll just wrap up, and I'm happy to talk with you later if you want to see some of the other details. So it turns out that in the literature there are actually two different notions of look ahead, which I'm going to call context-independent look ahead and context-dependent look ahead. So here is the simple idea. So here is a GFG, which is drawn in a stylized way. Here is the grammar. So this is n goes to A, or the empty string, so A, empty string. And then here for S, I have two different productions. And notice that I have n being called in two different places in the grammar. So there's a red call, and then there is the blue call over here, right? It's just a stylized way of drawing the GFG. So what is the idea of look ahead? Well, the idea of look ahead is, suppose this is the point that I'm interested in computing look ahead for. What I want to know is, for a look ahead of, say, 2 symbols, if I'm here and I look ahead, what are the next 2 symbols that I'm going to encounter on paths that begin at P? So let's take a look at this. So if I'm over here, the next symbol that I'm going to see is going to be a Y, right? And then I'm going to make this call to N, and then over here I'll see A, so YA is in that look ahead set. Similarly, I can go Y and then come out over here, return there, and B. So YB is also in the look ahead set there. Does that make sense? So I'm just putting up a road sign over there saying beyond this point you will see either YA or YB depending upon which paths you follow down there. Similarly from here, you go to Z and then A, so ZA, or you go Z, you return, and then you see the A here. So in both cases, I see ZA. So now suppose you have a string ZAB, right? So you're over here, and you notice that because the first symbol is a Z, I don't even need to go down this way. I can simply go down there, right? So I can prune some paths out earlier than I could if I did not have this look-ahead information. It's like saying, if I want to go to the Alamo, this is the direction to go in. I shouldn't go in these other directions. Does that make sense? Look ahead? Okay. But now, there's an interesting twist to look ahead. Suppose I'm here, this point in the GFG. What is the look ahead there? 2 symbols of look ahead. Anybody want to? So the first symbol is going to be A. There's no choice from this point onwards. But what happens after that? Yeah, the point is depending upon whether I came here through the red call or the blue call, it's either going to be AA. So if on the red call, it's going to be AA. If I came in on the blue call, after the A, I'm going to go back there and I'll see a B, which is why I drew AB with a blue call over there. So this is an interesting point. So what it says is, look ahead at a given point in the GFG is a bit ambiguous, right? Because I need to tell you how I got to that particular point also. Again, because of this non-Markovian property of these paths that we are following. You're just not following a bunch of random paths. My history affects how these paths could evolve. This is called context dependence. And if you know interprocedural data flow analysis, this is exactly what we worry about. So context is simply the CR path that you have followed from start to the particular point where you're trying to compute the look ahead. So the simplest thing to do is to say, look, I'm not going to worry about context. I just want to know what all the possibilities are, right? So forget about how I came to P. Just tell me what might happen over here. And so that's a bit like erasing these colors over here and just saying the look ahead here is AA or AB, right? That's the look ahead set. Similarly for this. So that's a bit bigger, right? The look ahead set then is a bit bigger than if you actually used the context information. Because if I also told you, oh, by the way, when I'm going to look up the context information, right, the look ahead information at this point, I'm going to tell you that I came here on the red call. So then you should only return AA because that's actually what's relevant to you, right? Obviously, that's going to require much more work, right? But that's called context-dependent look ahead. And the simpler one is called context-independent look ahead. And it turns out that SLL and SLR, simple LL, simple LR, if you know those terms, as well as Earley. So the way I described Earley to you, there was no look ahead, but in Earley's original paper, he does have some look ahead. What all of these guys use is this simple notion of look ahead. Back when Earley was doing his work, this was all that people understood. And so they only use this context-independent look ahead or simple look ahead. If you know LL and LR as opposed to SLL and SLR, well, LL and LR actually use context-dependent look ahead. So when these parsers want look ahead at a particular point, they also tell you what the path is that has been followed from start, and they use that to index into this look ahead set to give you precisely the look ahead for that particular context. Okay, is the intuitive idea clear? Okay. And then there's a question of how one goes about computing these things, and it turns out it's a very simple, what's called an interprocedural backward data flow analysis. And for handling the context-dependent look ahead, you have to do something called cloning, which you may be talking about in your compiler class towards the end. So yeah, that's really what you do. Okay, and then we get to these LL and LR grammar classes. But I'm going to skip LL and LR. I'm happy to leave these slides. And also, as I said, we have a paper. What I want to do is finish up by showing you a little cute result that those of you who know some programming languages might appreciate. So one of the things that we said in the standard presentation becomes obscure is we know every regular grammar is also a context-free grammar, and yet the way we think about parsing regular grammars, namely with a non-deterministic finite-state automaton, is very different from the way we handle context-free grammars. But you could argue, well, the same thing is true here also, because if I give you a regular grammar, like this one over here, so this is a regular grammar, well, here is a NFA that you would draw for it using the standard algorithm, and the NFA is one graph. But if you drew the GFG would look something like this. I've removed a lot of labels and so on, but you can see dot S goes to A, so that's S goes to A, and then B followed by A, right? So this is the GFG. So you can say, but you know, you're cheating too, right? You have two different graphs. So if you really have a nice unified theory, somehow these two graphs should end up looking the same, right? So why do they look so different? So here's a cute result. It turns out that if you have a regular grammar, which is what's called a right linear grammar. So in other words, in a right linear grammar, the non-terminal only occurs in the tail position, the very last symbol. If there's a non-terminal at all on the right-hand side, it occurs as the very last symbol. Okay, so that's called a right linear grammar. And for every regular language, there is actually a right linear grammar. You can show that. Right? So this is a right linear grammar. So now let's take this GFG over here, and let's take a look at what happens if I happen to follow this particular path. If I follow this path, this is the call node to A. So what I would do is to push that return node. But if A is the very last thing in the sequence that I have on the right-hand side, I can do what's called tail call optimization. So you know tail call continuation, passing style, tail call optimization. The point is you don't ever need to return to the point after A because all you do is return from there to wherever S was called from. So you can actually optimize away this call and not push the return node at all over here. So in other words, this just becomes an ordinary edge, and you don't need to push anything on the stack. And so it turns out you never push anything on the stack, and you never pop anything from the stack if you happen to have a right linear grammar. And so what you can do is simply optimize those edges away and say these are not call and return edges, these are simply epsilon transition edges. And you don't need the stack at all because you never push anything on the stack. Every call is in the tail position, right? That's the right linear grammar. So you never push anything on the stack, and you never pop anything from the stack either, so you dispose of the stack. And so you've optimized away the stack. Call return edges just become epsilon edges, and then the GFG just becomes a NFA. And as you can see, this NFA now, if I just simply eliminate some of these epsilon edges, actually becomes the NFA over here. So there's a simple motto then. So the GFG of a right linear grammar together with tail call optimization. So if you know scheme compilation and so on, is one of the standard optimizations that's done. So GFG of a right linear grammar plus tail call optimization simply gives you the NFA of a right linear grammar. So there's a nice unification there that passes through some compiler optimization technology as well. Yeah?
On the graph on the right, where did those nodes where it's all epsilon around it come from?
This was the original GFG.
Right, but I mean, how did those get translated from the grammar?
Using my GFG rules, right? So A goes to C followed by A. So that's A goes to C followed by a call to A, right? And similarly, A goes to epsilon, that's just this. S goes to A is that, and so on. So I just followed my GFG rules and built this. But the GFG is different from an NFA. What I'm saying is, if you use tail call optimization, then basically the stack disappears, because every call, every non-terminal, there's only one at most one non-terminal in each rule, and it always occurs at the tail position. So you never have to push anything on the stack, you never pop anything from the stack. So these special edges, the call return edges, just become epsilon edges. That becomes an NFA, and that's how you do the unification with regular grammars. Okay? So there's a lot of stuff over here. Okay, let me skip over this. Here's what I told you. So GFG, graphical representation of any context-free grammar, could be ambiguous, whatever. I just build this graph. I follow paths in this graph. The Earley parser is a simple extension of the NFA closure algorithm. Look ahead, LL, LR, all of these things work out very easily. So I want to finish up by telling you a story about Panini's grammar. So we began about an hour ago by recalling the contributions of the great Sanskrit grammarian Panini. And so this is also a story about Panini's grammar, but it's about the composition of a very famous Hindu hymn, which is called the Bhaja Govindam. And it was written by Adi Shankara, who was one of the great gurus of Hinduism, who around 800 AD, he led a great revival of Hinduism in India. And so the story goes, he didn't look like that. That's, just a random picture of some guy. But so the story goes that one day Adi Shankara and his pupils were in Benares walking along the banks of the Ganges River when they saw an old professor of Sanskrit sitting under a tree and reading Panini's grammar. He's an old professor, right? I'm becoming an old professor. I know what that's like. So, you could still go read papers and so on. And so this guy was apparently sitting, reading Panini's grammar, trying to understand some details and so on. And Adi Shankara was apparently overcome with compassion for the futility of what this old man was doing. He really ought to be thinking about the afterlife, and there he was trying to understand the rules of grammar. And so he composed the Bhaja Govindam as advice or a rebuke, really, to this old professor of Sanskrit. So I'll read the first sloka out to you in Sanskrit, and just to give you the flavor of the language, and then I'll translate it to English for you. So the first sloka goes, Bhaja Govindam, Govindam Bhaja Mudamate, Samprapte Sannihite Kale, Nahi Nahi Rakshati Dukring Karane, which if you translate into English and take a little bit of license to make all the concepts accessible, Adi Shankara's advice to this old professor of Sanskrit goes, adore the Lord, adore the Lord, adore the Lord, you fool. When death comes at its appointed time, the rules of grammar, Panini's grammar, will not save you. Thank you for your attention.